Hello, my name is David Santiago Barajas Quiroga, and now I'm gonna to present this article. Okay, the article analysis of the goodness of fire of the SAM model for the calculation of the removal percentage of flocculent particles with low initial turbidity values in the problem water. First, I will explain the context of the study and why this topic is important. Then I will move through the objective, the methodology, the results, and the final conclusions. Okay, now first, why this article matters. Okay, this topic matters. This article is important because water treatment plants often recycle water with low turbidity, especially in mountainous regions. Under those conditions, flocculation and sedimentation behave differently, and the removal of particles become harder to predict. The matters in practice because operators need reliable models to support decisions about treatment performance. The authors of the study were some models still works properly in that kind of water, which makes the paper directly relevant to real operating conditions. Okay, this is a reason because this study is important. Okay, yeah, relevant. So for another part, we can see your objective. And your objective is so simple. The objective of the study is to evaluate the goodness of file of some models using the coefficient of determination or R square term. In simple words, the researchers want to know how the model is to the real experimental data when the initial turbidity is low. That is a very practical question because a model can be mathematically elegant but still file it doesn't not much really will notch. In the article, a value above 0.90 is considered a good find, so that threshold becomes the reference point um, for interpretation of the results. Okay, now we pass at the methodology. First, the authors analyzed historical turbidity data from for drinking water treatment plants in Cundinamarca, Colombia. And then they prepared the laboratory test water within observing range. After that, they use a jar test to identify the optimal alum dose applied to the coagulation, flocculation, sedimentation process and measure the remaining turbidity at different depths and times. And finally, like we can to see that, so here in the presentation, they find the data with multiple linear regression to obtain the model parameters and the R square term value. So the methodology moves from real file data to controlled laboratory testing and then to statistical modeling. That would be the methodology that they use it for that. Okay, and now we can to go to add this more explain it. Like we can to see for here in this page. So a model is a mathematical equation used to estimate the percentage of flocculent particle removal. It connects removal percentage with sedimentation, time, and depth, which make it useful for describing setting behavior. The practical advantage is speed. Engineers can estimate performance without drawing the full graphical methodology every time. However, however, the model is only useful when the experimental data follow a stable pattern. In that sense, the model is helpful, but it still depends on the quality and the regularity of the water behavior being analyzed. Okay, that will be the some model. So we can to follow the historical data pattern. Okay, that will be that. Like we can to see here in this graphic that now I will explain what do we can have here. The historical data show that the most of the raw water samples had low turbidity values. This is important because it meant the study that reflects real operation conditions in clear mountain waters, not only in a laboratory case that isn't a result good. Not the chart on this slide shows that the vast majority of values were below 15.5 NTU. That concentration of observation in the low range is exactly what makes the article useful. Okay? It tests the model in the zone where the prediction is usually more difficult, and we can see that here there is more easy, like this graphic. So for another part, we have here there is the goodness of file results. The result shows that the model performance poorly at very turbidity values in the improves as turbidity increases. The reported R square 2 values are below 0.90 for the lowest turbidity layers, while the higher values approach or pass the advanced threshold. In other words, or for more easy, the Samuel becomes more reliable only when the word is slightly less clear. Okay, when it's clear more easily. And so here in this page, why doesn't this happen? Because low turbidity water has fewer particles, flux form less strongly, and the sailing pattern becomes irregular. That irregular behavior makes it difficult for one equation. Okay, it's more difficult because for the because it's irregular. And for one equation to capture the whole process. So the main conclusion is that some model that isn't universal. It depends only the turbidity range. Okay. And now for finish, we have the conclusions. So the article concludes that the sun models doesn't provide a strong fight for very low initial turbidity values. Its performance improves as turbidity increase, but the low turbidity range remains a limitation for practical engineering. This means the model should be careful, not automatically. Okay? No, it's automatically. And the author suggests that the models or adjustment should be tested for this condition, especially if the plant works regularly with very clear water. Yeah, and now for finish or for close to finish to study, it's useful. This study is useful because it shows the limits of a common sedimentation model under real low turbidity conditions. It is uh, it is a good example of how engineering Models must always be checked against actual data. Okay, thank you for your attention and goodbye.